What is dishing?
So sir, we do CMP, chemical polishing after depositing each layer of any metal or the oxide. So after that, so basically there is some amount of dishing that happens in the copper since it is very ductile. So this kind of small tubs or maybe
Okay. Thank you, Gagandeep. So what is happening over here is that, oh yeah, this thing has again got stuck, it seems. Just give me a moment. So when we do the fabrication process, when we are fabricating devices or whatever, so what happens is that at some point of time, you will do chemomechanical polishing, in which what we essentially do is we flatten out the surfaces. Okay. And in that flattening out the surfaces, there is a mechanical force that is also applied. So when that mechanical force is applied, so when we are polishing, so this is the surface of the wafer and we are kind of applying some mechanical force, scrubbing it also. So what happens when you're scrubbing the floor or something? The dirt or the uneven surface on the top will become polished, will move out, and you will have something which is clean, stable, flat. Now, if the surface that you are polishing is, how do we put it? If the surface that you're polishing is of same mechanical strength, then what happens? Then when you polish, everywhere the depth or the amount of surface removed from the top is almost the same. What does that mean? That means that your surface remains flat. However, in copper, we understand that we also have this thin layer of barrier that is put around the a thin layer of barrier that is put around copper. You remember that?
Yes, sir.
So this barrier has much higher mechanical strength than copper. So what does this do? This barrier then starts to stay strong, whereas other parts of the system kind of get scrubbed. Okay. So I'm trying to bring my slides back to you, but it's somehow not working. So I wanted to show that to you. Otherwise, I will go to whiteboard and show it. So you're able to see my whiteboard?
Yes, sir. Yes.
So what is happening here is that you have this copper barrier. Hello, क्या हो रहा है? So you have this copper barrier. Arey, I think they don't want, the system doesn't want me to take thing up. Huh? So I have this copper barrier, and I have filled copper inside it. Let's use a color there. I have filled copper inside it. Inside it means I just did the deposition of copper filled everywhere. And over here, I also have what I call as silicon dioxide. Okay. So this region is silicon dioxide. You are able to see this? आप इसको appreciate कर पा रहे हो? Silicon dioxide के अंदर हम trenches बनाते हैं to deposit copper and make copper wires. All this we've discussed in the fabrication wala section. So we deposited copper and now we want to remove the excess copper. So what we do is we run a CMP process through which we say this extra copper will get removed. And as we do it, we understand there is one mechanical strength of the oxide, there is another mechanical strength of the copper, and there's a very different mechanical strength with which the barrier holds its level. So what happens is that if I have a very thin wire, it works fine. Consider a case I have a very wide wire. There is oxide here, there is oxide here, and there is copper that is filled here. So in a very thin wire, a CMP machine will come. A CMP machine, let me show it with what color? Let me show it with green color over here. Okay. The CMP machine would come, and with this barrier and with this barrier, it will kind of stop there itself. Whereas when it is a thick metal wire, then the CMP machine, this barrier will stop it from going deeper. Over here also on the edge, the barrier will stop it from scraping extra copper. But in the middle, because copper is much softer than the barrier and you are applying some particular force, the CMP machine will go deeper. So the final copper that you will get is not a flat metal there. Okay. The final copper that you will get will have this kind of a structure. Hello. Okay. So this is called as dishing. Okay. So are you able to realize what is happening? If dishing happens, are you okay with it? Or is there some challenge that you will face as a circuit designer?
So resistance of wires increase.
Yes. See, you've made a wide wire. What was the purpose of making a wide wire? Because you wanted its resistance to be less. But what happened? Because you made a wide wire, there was dishing that happened, and the effective resistance did not decrease as much as you wanted it to.
Sir?
Yes.
Sir, but like when you're discussing the wires, so there was one concept was used aspect ratio, and in that you said that for the advanced technologies that is higher. So by that mean this basically T would be much higher than the width. So this basically effect should be less in advanced technologies.
Yeah, that is the case. Now we're talking about the same technology. See over here, the width is so much lesser than the height, is it not?
Yes, sir.
So this width is, let us say, 50 nanometer.
Okay.
But this width that I'm talking about is 1 micron. So when the width is 1 micron, the depth will not change. Na? Depth to technology ki utni hi rahegi.
So sir, but the 1 micron, you're talking about so these are different metal layers you're talking about. Right?
No. Same metal. You can make wider metals than the minimum DRC, na?
Yes, sir. So but
So
then
I've just made a wider metal so that I have lesser resistance.
So but then when the width is 1 micron, then the height will be also much more than that. So the aspect ratio of air is maintained.
So what can you maintain in a technology? Can you maintain the depth in which you will make the holes in silicon dioxide, or you will be able to maintain the aspect ratio? What is it that you will maintain in the technology? You've seen the fabrication process, hai na? We've covered the fabrication process. So what was the fabrication process? We said we will deposit oxide, then we will put masks at some places, and then we will expose UV radiations. We will do something. At some places the mask would remain, other places the mask would not remain. So wherever the mask remained, let us say, we would now make holes. So would you now decide to make holes based on the size of the mask, or you will make holes based on your technology specifications?
Masks.
Mask say. So if I have a wider hole, you say I will go deeper.
Oh, depth is not dependent on mask. Like
Depth cannot be dependent on mask.
yeah, only the width which we are width of the mask which you are placing that.
Hai na?
Yeah.
So that is what I am saying. This depth is fixed.
So, sir, for a particular technology, that aspect ratio doesn't have to remain the same for like that you're saying. That is a disagreement.
Aspect ratio for the minimum wire will remain constant for the technology. But for the minimum wire, we always talk, when we talked about aspect ratio, we were talking about minimum wires placed next to each other. But not, you will not make only minimum wires in your designs, na? You are worried about resistances.
Okay, so like as I go up the metal layers, then the aspect ratio won't remain.
No, I'm not even talking about up the metal layers. I'm
Okay.
simply talking about even in your standard cell. When you are making those VDD and GND rails, I said they are 2x the minimum width. Did I not say that?
Yes, yes, sir.
So do you think the depth will also be twice?
So I mean depth is decided by the technology, right?
The depth will remain same, na?
Yeah, yeah.
So if depth remains same, what happens for very wide wires? This is how it would appear like.
Yeah. Okay, so aspect ratio was only for the minimum kind of basically to give a
So
understanding.
aspect ratio का भी मतलब नहीं है. We
Okay.
just say this is the thickness of the wire. That is how we calculate the sheet resistance, na?
Yeah,
Remember,
yes. Yes, sir.
sheet resistance was rho by H.
Yeah.
This is H. Now that will not change depending whether your wire is thicker or thinner.
Yes, sir.
है ना? This H remains constant. This is H here and this is H here.
Yes.
Both the places.
Yes, sir.
Okay. So now what do? You do not want this dishing. Itna clear ho gaya. We do not want this dishing to happen. So what do? What can you do? चलो आप अगर होते तो आप क्या करते? Physically सोचो. Ranjit, you were saying something.
Sir, we should go for a less wider wire.
No, but then the resistance would anyways increase. I want low resistance only.
Sir, if the width is reduced, then the resistance, okay, yeah, resistance again increases. Yes. Yes, sir.
Don't polish it near the हम लाइक जहाँ पर भी हमको ये कॉपर रहता है ना उसको पॉलिश नहीं करना है.
So how do I know? मेरे को तो माइक्रोन लेवल पे पॉली की ये कॉपर की डेंसिटी फर्क हो जाएगी. आप you have got any polishing done on your home floors?
Yes, sir. Yes, sir.
Is it easy to say कि नहीं मेरे को इस वाले पत्थर को नहीं करना, उस वाले को करना है? The machine would simply run ना all over.
Yes, sir.
So it would run. What can you do?
Yeah, sir. As shown in the image, we can just make it as a different tub. Upper side it should be small and the lower side it should be big.
नहीं should be तो फिर resistance बढ़ गया ना. You wanted to have a wide wire so that your resistance reduces. But यहाँ तो resistance वापस बढ़ गया. What do? We don't want this. Introduce more barrier. Wow. Good, Nikhil. How do we introduce more barrier? You're going in the right direction, Nikhil. क्या करोगे? अगर आपका ये घर ही हो, let us say this is our house. We want to make the roof now, and the roof is sagging. What do?
सर एक पिलर सपोर्ट दे देते हैं बीच में.
You will put a
between
pillar in
barrier.
between. Yes. You will put a pillar in between. So what is done then is that in the metals, when I have very wide metals running, there is a DRC that you will see which is called as slotting. So I have to make such slots, very thin slots. Okay. So what happens? I get oxide and barrier over here, both. Okay. And they give the required mechanical strength to my system. Okay, this is called as slotting.
So, but how did this solve the problem? Because then it is again reducing the copper area. Then.
Yeah, but effectively what happens is that the copper area reduces only by this much. And that too not always. Do you realize this? Over here, I still get full width. So what happens is that after slotting, you will see that this width, this depth will not happen. It will be almost, okay, so what will happen is this, let me use the same color. This will be now almost like this, just that in between there is some little block somewhere. So effectively, your width was then not 1 micron. Your width was, let us say 0.98 micron. But what we were experiencing earlier was that overall resistance has increased by more than 40% also because of dishing. So आपने 1 बनाया लेकिन बना 0.6. Now by using the slotting, you will limited it to only 2 to 3%. So there is a loss. Clearly there is a loss, but it is much lesser than the loss you would get because of dishing.
So,
Yes.
sir, in a technology, when we define the width of wire width, so that is dependent upon how fine things I can make on the silicon.
That
So,
is
sir,
the minimum wire width.
yes, sir. So, sir, this barrier would also have some DRC.
Yes.
So, sir,
Yeah. So there is DRC linked to slotting. You will see that.
sir, does that not really stretch the limits of technology, I mean, in which I am
So be
making?
it. So be it. We are a designer. We can ask for anything under the sun. Let's do that. We are a, आप डिजाइनर है ना, आपको कुछ चाहिए आप तो मांगोगे. Let the technology team enable it. जब टेक्नोलॉजी टीम अपने हाथ खड़े कर दे, no we can't do it, then we will see. Okay, chalo. So thank you guys. We will start with the inverter part in the next class, and thanks for a very good candid discussion today. And I hope this turns out to be a very good learning experience for all of us. Okay,
Sir,
yes,
sir, the slotting that we are doing in this copper wire, sir, is it on the surface or it is inside the copper?
inside the copper. I make barriers over here. So I'll make thin oxides, oxide pillars in between. Okay, so this is top view. And this is, you may say, cross-section view.
So, sir,
Yes.
yeah, so, sir, can we do anything else? I mean, like, we are doing slotting to avoid dishing. So, can we do something like we can use like the polishing thing you said with something which doesn't like give us this this concave or this shape in the copper? I mean, it flattens it completely. I mean,
Yeah,
like,
that would be nice. That would be
yeah,
nice,
so
but we don't have that kind of technology yet.
okay.
And this is also cheap enough. So that is what is implemented.
Yeah.
Sir,
Mhm.
sir, in the slotting that four structures that we made inside the copper, sir, couldn't we made just the structure that was effectively appearing on the surface so that the effective width for the CMP machine would have decreased, but overall
Yeah.
area inside
How would you
copper would have.
manufacture it, Shivam? Shivam, the question is, how would you manufacture it?
Sir, still we are using some technique to manufacture this.
No. This
So
is like growing oxide, making holes around oxide. This is the standard process. Now you are saying that, okay, I have processes to make these holes. I also want some floating stuff to be made there now. How would you make that floating stuff there?
sir, it is still made in this four slotting diagram that you shown to us.
I'm sorry, there is some fumigation going on at my place. Yeah, you're saying something, Raghav, Shivam?
Sir, it was still made, sir, in the four slotting diagram. So can't we just remove those three slotting points inside the copper?
No, they're not made on the surface, Shivam. They are made in the copper. In this copper, you will have to have this barrier there. This barrier will give the mechanical strength, and there will be oxide inside it. So it will actually be in the copper. You'll have copper on all sides, and this is what will happen. This is how it will appear. This cross section.
Okay, sir.
Sir, this barrier would also be a conducting but harder metal, right?
Barrier is very resistive. It does not conduct as good as copper.
Okay.
It is very resistive.
Sir? Sir?
Yes, Momin?
Sir, after slotting, will this not affect the resistance of the wire? Because we have introduced these.
Yeah, वही हमने बात करी ना. Momin, when we said this, that the effective bit now is 0.98 instead of 0.6.
Okay, so we are compensating by this.
So it impacts the resistance, but much lesser than dishing.
Okay.
Sir? Hello?
Yeah.
Yes, sir. So, sir, when you were presenting the slide, sir, I saw that the barrier was a bit of in triangular shape, or it was not in rectangle, but it was a trapezoid.
Yeah, that is a fabrication inaccuracy. Don't worry about that.
Okay, sir. Thank you.
It is not intended to be that. It becomes that because of fabrication inaccuracy.
Okay, thank you.